so I don't keep waiting. Daniel, can you see my screen?
Yes, I can.
Okay, thank you. Okay,
Yes,
it's as
ma'am.
if I have to like beg you people to answer me sometimes. Okay,
Sorry
so
about
thank you
that.
very much. No, it's fine. So just answer me when I ask questions like that. I don't want to waste so much time. So just answer me when I have questions like that. And if there's anybody that cannot see my screen or believes that what he's saying is wrong, you can definitely let me know. So linear regression in R. We've done scatter plots. So from scatter plots, you should be able to understand what linear regression is, because it's a line that shows the best fit of your data points on a scatter plot. So you have a scatter plot that you plot like the way you plot points on the graph, right? A scatter plot, and then there's a line that goes through this point and shows how well correlated your data is. That is a regression line, basically. So regression line is a statistical procedure, or linear regression is a statistical procedure that is used to predict the value of a dependent variable known as the response variable. So the dependent variable is y, and the independent variable is usually x. It can be anything, but then statisticians have registered the y and x values inside our head. So it's just y and x. Okay, so y is your dependent or response variable. Yx can be one or more, and it is your predictor or independent or explanatory variable. So a procedure that helps you to determine this relationship between both of these variables I just mentioned is called linear regression. And then we have two types of it. We have simple and multiple linear regressions. Linear regression, yes. So oh, I thought I went to the next slide already. It's quite slow. I don't know why this is not changing. Okay, it's changing. It's just slow. This is quite slow. Oh, where's my network? Sorry, I'm just trying to see that my network is working well. This is slow. Trying to go to the previous page, and it's quite slow. Okay, simple linear regression is used to find the relationship between a continuous dependent variable y and a continuous independent variable x. Like, when you're plotting scatter plots, you use two continuous variables, okay? So, and then x is the independent variable and y is the dependent variable. So a simple linear regression model helps you to find the relationship between a dependent variable y and one independent variable x. Multiple does for two or more independent variable x. So for multiple, we have x1, x2 to xn, like different variables that help you to predict the outcome of y. While in simple, you have just one. And this is the linear regression model. This is what it looks like. And then this E is the residual. So it's like the error that's generated from the data points, deviation from the regression line. So definitely all your data points cannot be on the regression line, or cannot be well correlated with the regression line. So a line just goes through, and then you have some extreme values that are not very, very well circulated around the regression line. So this is where the residual comes in. So and then we have these values. These are parameters, and the x is your independent variable. So this is a simple linear regression model. Okay, and it's explained here. Okay, B0 and B1 are regression coefficients. They are regression coefficients, and EI is the error in the measurement of the ith value of x. So the values of x, the residuals in the values of x is denoted by E. Regression is a very wide topic. Linear regression is a very wide topic. We might not be able to cover everything that is all about regression, but then I would try my possible best to explain the basics. So multiple linear regression model, like I said, we have more than one x values, more independent or predictor variables. So this is x2, this is x2, and then we could have it up to xn, and this is the residual for the ith value of x, or yes, whatever value of x it is. So this is residual, just as we had in the former one in the simple linear. This would go for all of the residuals of x. So a multiple linear regression model with two explanatory variables. So this has two explanatory variables, x1 and x2. Okay, not x1. This should be x2. So this is the formula for a multiple linear regression model. So we have something called least square estimation method, and this is the method that you use to fit your regression model for a given set of data. So when you have a set of data, the method you use when you're trying to fit a regression line for a given set of data is called the least square estimation method, and it helps you to determine the best fit line for your data. So you have a number of data points on your chart, and you want to determine the best fit line for your data. The least square estimation method is used for doing that. And then you use this is the formula that is used to find out the best fit line in regression analysis. It's called the sum of squares of residuals, and this is how to calculate it. It is the square of the excess value. That's the e. It's square of e. So sum of all the e's is the square of the e's, and then the sum of it is what gives you this SSR, which is the sum of squares of residuals. This is a lot of formulas, right? We might not really point into all the formulas, but if you were working manually and not with programming, you would have to use all of these formulas. But we're going to be using programming to do all of this. So, but the reason for trying to learn all of this is you want to understand the basics of regression and not just jump into programming everything out. So that's why we are trying to look at these formulas and the meanings of all of these terms. So manually, this is the formula you would use. If you did statistics in school, you would have an idea of these things I'm saying, things like regression line and all of that. So these are the formulas you use to calculate them manually, but in programming, you do not have to directly specify or write out these formulas to get your results. You can just do this with some inbuilt functions in R. So like we said here, this is E. So definitely E would be yi minus this plus this. So this coming to this side is what gives us this. So that's why we have this all squared. So this is how to calculate the sum of squares of residuals. E is the error, y and x are the variables, and b0 and b1 are coefficients. So that's that about the least square estimation method. This thing is quite slow. So these b0 and b1 are parameters that you can find with some calculations. Doing some calculations, you'll be able to get these parameters. But for the purpose of this class, we'll not be doing the extremely long calculation. It's a very long calculation, so we'll not be doing that. I don't know why this is slow. Okay. I don't know why it's slow. My network is slow. Okay, so let me just reconnect. Please confirm that you can see my screen and hear me.
Yes, you can see your screen and hear you clearly. Please go ahead.
Okay. Okay. I'm just trying to understand why his network is slow. don't know. It's slowing. Okay, so let me just talk from the textbook. Okay, so there's something called R adjusted checking model accuracy. Okay, it's up, checking model accuracy. Okay, and statisticians usually use this to calculate the adequacy of their regression model. So you want to see how adequate your regression model is. The R squared is usually used to calculate this. So we have R squared and adjusted R squared model methods, and both of them are used to check the adequacy of your model. So you did a regression model and you want to see how adequate and correct it is. The R squared or the adjusted R squared methods are used to do this. Okay, so when you have a low R squared value, it means you have high variance. That means your data is very it's not well correlated. There's a lot of variance in your data. But then when you have a high R squared values, R squared value, it means that you have low variance. Okay, and one thing we should try to check for in our data is low variance. Your data should not have a huge variance, right? So that's what R squared value is used to check. So it helps you check how adequate your model is. And then this is the formula for calculating it. SSR over SST, where SSR is the sum of squares of residuals, and SST is the total sum of squares. And there's a way you calculate the total sum of squares. Total sum of squares is summation of yi minus y bar. So, okay, it's not here. So yi is, they are all the values of y. If you are on your textbook, you can follow your textbook to see these formulas I'm talking about. Let me see. Just in case you are very curious and you want to see the formulas, I'm using my mouth to just mention. There's no board, so I have to just say them with my mouth. But then if you're very curious and you want to see what I'm saying, page 9. So I'm on page 9 currently. So SST is summation of, so you take all the yi's, you subtract the mean value of y from each of the yi's. Okay, so maybe y1, you subtract the mean value of y from y1, what you get, you add it to y2, subtracting the mean value of y from it, you add it then up like that, then you add everything together and find the square. So, or find the square of each of them first before you add everything together. So subtracting the mean value from each of the y values, squaring these values and adding them together is what gives us the sum, the total sum of squares. And I've told us the sum of square of residuals already. I've given us formula for that. So that is the way you calculate R square manually. And then this helps you to determine how well varied or how less varied or more varied your data points are. So R square normally ranges between 0 and 1. So when you have 0, it means no correlation. When you have 1, it means exact relationship, which is very hard to see in data points. When you're plotting y against x, it's so difficult to see straight line unless they are like the same data, basically, unless x and y are exact same data point. That is, x1 and y1 is the same thing, x2 and y2 is the same thing, and all. That's when you have an exact linear relationship. So when you have R squared equal to 1, it means you have an exact linear relationship. When you have it equal to 0, it means no correlation. So most of the time, your R square falls between 0 and 1. So when you have your R square above 0.5, you know you have a good data correlation, good correlation between your variables, between x and y. So that's about R square value. And this is how to calculate the adjusted R squared value. It's calculated when you update, when you add new variables to your data. So when you add new variables to your data, this is what you should use to calculate your R squared value. So these are just the manual explanations and the basic explanations of linear regression and the formulas that are used to calculate them. K is the number of parameters you have, and then N is the number of observations. So that is about calculating R squared, which we'll not be doing manually, but then you still have to understand, have a basic knowledge of these things. So it's slow again. Okay, let me just continue talking. Okay. I don't know why it's slow. Okay, so regression assumptions. The validity of a regression model is ensured by statisticians when building the model on the basis of certain assumptions. So these are the type of things you use to check, or these are the various terms that you have to consider when you are creating a regression model. Okay, so to know that your regression model is valid, these are the assumptions that a statistician will look at. So linearity, there must be a linear relationship between the dependent and independent variables. It assumes a linear relationship. Okay, so these are some of the assumptions. That means in regression, they are assuming that there exists a linear relationship between the dependent and independent variables. So by linear relationship, it doesn't mean that all the points have to lie on the exact same line, but there should be a form of linear relationship. That is, you should be able to establish a linear relationship between your x and y variable. Independence, there is no correlation in the errors of the collected samples. So the samples you collected, that is, you don't have the same errors. Like there's no correlation in their errors. Their errors are independent of one another. So the errors are not, they are biased. They are not exactly correlated to one another because you collected samples of data. So your errors should not be correlated because when you are sampling, you are sampling randomly. So then that means if you're having errors, then the errors too should be random. So independence in the errors. If you want to know more about these things, you just have to check them up. But then I'm trying my best to explain very fast and still do the explanation at the same time. Homoscedasticity. This is so difficult for me to pronounce. Homoscedasticity assumes constant variation in errors. So that is your errors are okay, it's similar to the first one, okay, but then this means that their errors will also always change. There will always be variation in your errors, in the errors in your data. So if you add a new data point, you would have a variation in your error. Your error from before cannot be the same error now because you've added a new data point. Sorry about this. So normality assumes normal distribution of errors in the collected samples. So you know what normal distribution is, okay? So there's a normal distribution of errors. That is, it takes a particular kind of curve. Your errors take a particular kind of curve. So all of these things are the assumptions that a statistician has in his mind when he's performing a regression model. And then these things I used to check that your regression model is actually valid or not. A lot of details on these things, you can still check them out, but then there are so many details on these things which you might not be able to cover completely in the class for today. But definitely, like I used to say, you can check them up if you want. So multicollinearity, that's what we're going into next. Multicollinearity. Multicollinearity is when you have an exact relationship between two explanatory variables. So for example, you have two, okay, like I said we have linear regression models, right? We have simple and multiple. So in your multiple regression model, you can have two or more explanatory variables, like I said. And then if you have two explanatory variables and the two of them are well correlated, then why do you have two? Why not just have one? So that is multicollinearity. So if you really want to make use of two explanatory variables, that is two independent variables, two x values, then they should not be directly correlated with one another. So when they're directly correlated with one another, it means you are having multicollinearity. So collinearity, multicollinearity, which is wrong. So you have to check for this, or take only one x value, or take only the ones that are not completely correlated with one another or nearly correlated with one another, because there's no point having two x values that are almost the same and then you're plotting them against the y value. It's like doing the same thing. So why not just use one of the x values? So that is what multicollinearity is about. Factors that can make multicollinearity exist. I don't know why my slide is doing like this. I really do not understand. It's today that I'm rushing now that my slide has decided to act this way. I don't know why. Or my network. Will I say my network now? Probably if I try to switch off and switch on my phone, but then I don't have time to do that right now. So this is the formula for multicollinearity. This is what you use to calculate multicollinearity, VIF. And VIF is, let me quickly check the meaning of that. VIF, variance inflation factor. So if your variance inflation factor is above 5, that means your your multicollinearity is high. So if you have variance inflation factor above 5, so that means you should check your data. You have multicollinearity, and multicollinearity is wrong. You shouldn't have it in your data. It is wrong. So R is still your normal R regression coefficient. Your normal R, right? That we talked about before. So 1 minus R square, 1 divided by 1 minus R square is your variance inflation factor. And when you have it above 5 and above, that means you have multicollinearity. Let me move to the next slide. Okay, so this is annoying me. Let me try to, I want to try out something. Please give me a minute. Okay, I'm back. Let me.
Sorry, that's VIF. The formula, the
Yes.
R squared, is this the same thing as the R squared we use in calculating that R squared and adjusted R squared? Is this still the same value?
Yes, it's the same thing.
Okay.
Yes, it's the same thing. So okay, so working with linear regression, right? I think that's the next piece. I'm sure you can still see my screen. I didn't stop sharing it. I thought I did. Yep. So okay, so working with linear regression. Okay, two numerical variables. Okay, like I said, regression is a straight line. Abi, yeah, I said that already. I think I described regression already. So regression line is a straight line that helps you show the relationship between x and y. And then definitely I've explained what x and y is. I said x is the independent and y is the dependent variable. So you use the values of x to predict the values of y. So the value of y is predicted based on a given value of x. X is called the explanatory variable and y is called the response variable. So how do you check linearity? You check this by creating a scatter plot. And this scatter plot, from this scatter plot, you create a linear pattern. So this helps you show the regression line for both variables. So a regression line is calculated by using y equals mx plus b. This might sound familiar to statisticians or mathematicians, or if you did maths, MTS 101 or something in university. So m is the slope, b is the intercept. So the point where the regression line crosses the y-axis is b, which is the y-intercept. So anywhere the regression line crosses the y-axis, it is called the y-intercept. And at that point, x is equal to 0. Because when you have a point on the y-axis, x will be equal to 0. So, and then m is the slope. So here, if you insert 0 here, you can see that y equal to b. So this is the y-intercept. So any point where x equal to 0, you have the y-intercept, which will be b. And okay, so that's basically about linear regression. Oh, it has started again. Is it when I share my screen that it does this? No, my screen has been shared. Okay. So the y-intercept of the best fit line is obtained by subtracting the product of the slope and mean of x values from mean of y values. Okay, so this is very abstract. Slope is the change in y over change in x. I thought they would give us, they put a formula here, but then there's no formula on the screen. But then it's fine. Slope is change in y over change in x. Okay, so so for example, if you had 10 over 3, okay, it means that your change in y is 10 and your change in x is 3. So it means that as x increases by 3, that means as x moves towards the right by 3, y moves up or increases by 10. So that is what a slope is. In the context of regression, the slope is interpreted from change in y values with respect to change in x values. Okay, so that is what a slope is. And the y-intercept is sometimes meaningful and sometimes not. So there are some situations where the y-intercept is actually not useful. For example, if rain was falling, if you wanted to check how fast a plant grows with respect to rainfall, and then say your rain is y, okay, you want to predict okay, you want to predict y. Okay, what do? You predict y, right? And then x is your variable. So you want to check the growth of corn. Okay, x is the growth of corn. So you want to put the growth of one corn and use to predict rainfall. So you are checking x is your growth of the corn that you are planting, or the growth of any plants that you've planted. That is x. And then you are using the rate at which x grows to predict rainfall. Now, let's assume that x is equal to 0. That is no corn growth. You don't have any corn growth. That means your y is supposed to be something, right? You want to check when x equals to 0, what is the value of y? But when you don't have corn growth, it means that rain did not fall. So that means y2 is 0. So there are some times that using the y-intercept to make some predictions can be not useful. So it's not useful in some scenarios. For example, your only variable for making rainfall is the growth of for predicting rainfall is the growth of corn. We could have, assuming we had other factors to check rainfall, it would have been different. But assuming the only factor we had was checking the growth of the corn you planted, okay, and you want to use this to predict rainfall, and then you don't have any growth in your plant. So you now want to check what the value of y is, that is the y-intercept value. Normally, you don't have corn growth means that you don't have rainfall. So if you are checking for the value of y at that point, y2 will be 0 because there was no rainfall. So in that particular scenario, y-intercept might not be useful. But in a scenario where you are trying to predict coffee, the need for coffee in a particular match. I think the example, I got the example from your textbook. You're trying to predict coffee in a particular match. You're trying to predict if they would need coffee in that particular football game. And then your temperature can go as low as 0, right? Your temperature can go as low as 0. So it's possible that predicting coffee in that type of scenario can make sense. So okay, so the football match is happening in, say, Poland, right? And then you are trying to check the temperature at that particular time with respect to how much of coffee would be needed. Okay, so you can check the temperature can be 0, that is x can be 0. So x is your temperature, x can be 0, while you can still have a value for the y-intercept. So the y can be the y, which is the coffee, can be 2. So it means that, oh, okay, when my temperature is 0, I would have people request for 2 cups of coffee or something. So that is very, very practicable, or you can practicalize that in that scenario for the y-intercept value. But sometimes when x is 0, y has to be 0, which means that y-intercept is not useful in some situations and y-intercept is useful in some situations. So that is just what I'm trying to explain, that y-intercept could sometimes be meaningful and sometimes not. So when x is 0, that is when you have a y-intercept. So there are some situations where your x is 0 and then you cannot have a y-intercept value. your y has to be 0. So situations like that, the y-intercept is not useful. So that's basically what I'm trying to explain. And then we have to know the practical applications of the slope. So let me talk about the practical application of slope. So for example, you are checking the effect of a drug on. Okay, so for example, you are checking the effect of a particular drug on the pressure on a person. So you're checking the effect of a particular drug on the pressure, maybe the measured pressure on a particular human being's body. If you had a slope on your regression line that is minus 2.5, so you calculated the slope, you calculated change in y over change in x, and you have minus 2.5. Okay, so your y value is the pressure and your x value is the drug. So you are checking the effect of the drug and you are checking the value of y. So if I use this amount of drug, what would be my pressure? If I use this amount of x, which is the drug, what would be my pressure y? So if you had a slope of minus 2.5, it means that your pressure is decreasing by minus 2.5 when you have this particular amount of drug used. So that's just the meaning. So minus 2.5 still means minus 2.5 over 1. So when you have a slope of minus 2.5, it means minus 2.5 over 1. If you have a slope of 2, it means 2 over 1. So it means change in y, y changes by 2 when x changes by 1. If you have a slope of minus 2.5, it means y decreases by 2.5 when x increases by 1. If you had a slope of plus 6, it means as y is increasing by 6, x is increasing by 1. So that is about checking slopes, and then it could be very useful in different scenarios. The sign, whether negative or positive, of your slope determines whether y is increasing or decreasing at any particular point in time. So that's one application of slope, of checking, of using slopes. That is one practical application of using slopes. Okay, making proper predictions. So this thing is quite slow, so I'll just continue talking. So making proper predictions. So I've talked about outliers before. I've told us that outliers are points that fall outside the normal pattern. And okay, we've not gotten here. Outliers are values that fall outside the normal pattern. And I remember showing you a value on outliers, on how to determine outliers. So I will not dwell too much on that. So we also have something called residual. Residual is the numerical difference between the predicted value of y and the actual value of y. So the predicted value of y are the values of y on that straight regression line. Those are the predicted values of y. So the predicted values of y and the normal values of y, the difference between these 2 points is called a residual. So that is another term that you need to take note of. And then we have some functions in R that are very useful for linear regression. So we have the sum of x, it calculates sum of all x values. We have the sum of y. We have the sum of x squared, which is the sum of the squares of all the values of x. We have the sum of y squared, the sum of all the y values of all the squares of the values of y. And then we have sum of xy, which is the sum of the products of x and y. So multiplying all x's with all y's individually, the sum of this product is called the sum of xy. So these are some of the functions, famous functions used in R when doing regression modeling. And then we have some other calculations. For example, we have the corrected sum of squares. Sum of squares, this is the formula used for calculating it. And then we have the sum of products. This is the formula used for calculating it. But then you wouldn't use this when you are programming. There are some other formulas you use when you're programming. For example, for this SSX, which is the sum of squares, you just use the summation of x minus x bar square. That's what you use when you're using R. So like I said, this is for manual calculations. You wouldn't do this when you're programming. You would use some formulas because this would give you a rounded value. And then when you are programming, you want to have a very precise value. So you wouldn't use these formulas. Okay, so that is about that. The last page. Okay, the last page is not loading. Okay, I'm not sure if I'm on the last page. Okay, so we also have the sum of squares of errors, and this is how it is calculated: y minus a minus bx. So this is how it is, how the sum of squares of errors is calculated. There are other calculations in regression, like analysis of variance and so many others. There are so many formulas in regression. But then all of these formulas will not be useful when you are programming, because we have inbuilt functions used for calculating all of these things in R. So, but these are useful for understanding the basics of regression. So this is most likely some calculations, and I would like to join them with the lab work. So I just want to be sure. I'll preferably join them with the lab work because they are similar to what we have in the lab work already. Some calculation in the textbook. If you look at your textbook on from page 25, there's some calculations that were done, some regression calculations that were done, but then most of them are also in the lab work. So we'll be doing them in the lab work, and then I'll be explaining some of the terms too in the lab work. So basically what they did here is like a summary, is like an explanation to what's in the lab work. So if we do the lab work, we would get the explanations as they are done in the textbook. So we would be doing the lab work now, and then I'll be explaining any necessary term or any necessary function that you need to know that is used in the textbook. But still, you can decide to go through your textbook for those particular parts, the lab work, linear model result objects, from page 24. Some data sets were used, but I would just use the data set in the lab manual and use it to explain all of the concepts that were done in the textbook. So that should be what is on this slide, on this particular slide. And then we're going to be using R. So let's just, okay, yeah, so that's just it. All of these functions, like extracting the coefficient and all, we'll be doing them in the lab work. So we don't need to read them here, because reading them here is still the same thing as just doing them in the lab work. So let's just go to the lab work and perform these functions. So let's open our workstation. Let's open our workstation. I thought I opened it before. And please also try to read. Don't wait for the class all the time. Try to read up on your own before the class, after the class. Try to Google things that you do not understand. Those are the kind of things that will help you generally. Google things, check your textbooks, do the rest of the lab work and all of that. So I'm waiting for this to come up. Okay, so for our lab work, we'll be signing in as Hadoop, and then Hadoop is the password. So you can sign in as Hadoop, and the password is Hadoop. This thing is always detecting system problem. Okay, so we're going to use a data set called petrol data. That's what we're going to use. We're going to use petrol data, and we'll be doing this in R. Okay. So let's just create a new R script. Yeah. Okay. So we're going to be using petrol data. So let's see let's see petrol data. So we're going to be using this. Is it petrol consumption? Petrol consumption. So this is it. We're going to be using petrol consumption, and it's here. So you can decide to move this to a folder that you want. If you want to be sure of the data you used or not, your choice. But let me just quickly show you. If you know how to create a new directory, so I don't think I need to explain that. If you wanted to create a new directory, you can do that here on Hadoop if you wanted to, but still your choice. Okay, so and then we can put this into the new directory, this petrol consumption that we used. So if you want to move this, oh no, you know how to copy. I taught us how to copy some yesterday or sometime back. So if you want to move this, you can easily move this. But then let's just work with it from here. We can navigate it from here, but just to not waste time. Last class I taught us how to copy files. So you can easily copy this file into this folder if you want it to be in this folder. Your choice. It's your choice. But then let's just quickly make use of data. Let me not dwell too much on that. So we found the data, and then let's set our working directory to home/Hadoop. I'm on page 260 of your lab manual. Home/Hadoop. And let's copy that data. So petrol data, it's a CSV file, right? So we're going to use read.csv to read the file. And we're copying it from, we're already on home/Hadoop, so we're copying from data sets. Assuming we copy it to the graduate training folder, we have to navigate to the graduate training folder, but we didn't copy it, so I'm just going to do this. Then let's check petrol data. So this is what it looks like. This is the first 6 rows, and we can also view it if we want. So this is it. This is what the data looks like. So this is petrol data. So what are we asked to do? So let's see what we're asked to do in the lab. So we want to find the correlation between all of these data, all of these columns. Then we want to see the one we're going to work with. So let's check the correlation between all of them. So to find the correlation, we use COR. So we're checking the correlation between everything. So each of them will check correlation of A with B, C, and D, of B with A, C, and D. So like here, we check correlation of this with the rest of the data points, correlation of this with the rest of them, and on and all. So we're going to input all of the columns. Okay, they use just four columns here. So let's do petrol data. Then we're using column petrol tax cents per gallon. So petrol tax cents per gallon. Then we're also using petrol data average income dollars. We're also using petrol data, proportion pop drivers, and lastly, consume mil gallons. So we want to check correlation of all of these. So let's run this. Okay. Oh, I made a mistake. So data.frame. Yeah. Okay. So these are the correlation values. So let me quickly show us this here. So you can see petrol tax cents per gallon. The correlation of this with itself is 1, definitely. So like I told you, when you have correlation equal to 1, it means you have a straight linear relationship. So if you are correlating, as I said, multicollinearity is wrong, because multicollinearity means that you are checking the correlation between you have two explanatory variables that are the same, and you're checking the correlation between them, very close to 1. So you cannot have two explanatory variables. It wouldn't make sense to have them. So if you want to have different explanatory variables, they have to represent different things entirely, so that you'll be able to get good model fitting, not the same thing. So you see that this is 1 because it's the same thing. Then this with average income dollars is 0.08, which is not very well correlated, right? 0.08. Then it's very close to 0. Then we have this with this, we have negative. This has a negative strong correlation. This also has a negative strong correlation, stronger than this one. So you can have negative and positive correlation. That is, the graph can go this way or this way. And then for petrol data average income dollars, correlating it to itself is 1. This is very low, this is negative low, this is also low, and low correlation, low negative correlation. And okay, this is closer to 0 than this is. Okay, so this is stronger than this one is. Then petrol for proportion pop drivers licenses, this is very strong. So look at this, this is 0.8, this is 0.8. So this and this are positively correlated. As you can see, we have it at 0.8. So they are more positively correlated. They are very positively correlated. And if you check this against the same thing, it will also give you the same thing, because this checking pop drivers with consume mil gallons is this. So that means consume mil gallons with pop drivers will still give us the same thing. So let's do these two columns, since they are very correlated with one another. So that's the way to check correlation between two columns in a data set. Okay, so let's plot these two values together. So petrol data pop drivers licenses, and then petrol data consume mil gallons. Then let's use the color purple. You can also name it if you want. And you could name the X and Y axis if you want to. So that is going to be a long process for me. So let me not do that. Okay. So here, so you have this, right? So you see that this correlation is strong, just as indicated here. If you plotted some of these other ones, you would see what the correlation looks like. So you can go home. I said go home. We're not in the class, like a physical class, but then you can go back and check, plot these values against one another and see what they look like on the chart. So you have a more in-depth understanding of what these values mean. So when you have minus 0.7, what does it mean? How would the graph look like? So you can check all of this later. And we could also add a line to this. you could add a line to this. So the y value is consume milk gallons, right? So this, and then correlating with this, we want to check the line of regression. So you see, this is the regression line. You see, it is almost like 1. You know, 1 will go from both edges to both edges. See, very close, 0.85. So you see, this is positively correlated with one another. So that's how to check correlation between two variables in your data set. We could also check the coefficients and residual. So you can check all the other functions in your manual. If you want to check residual, yes, question.
Does that, okay, that able line you just drew, does he actually
Yes.
give the line of best fit, or you're still
Yes,
going to draw?
it gives the line of best fit. It's
But there's
used for
no way we can draw.
regression line.
Okay.
Huh?
There's a way we can draw it, and I feel it's going to cross more points compared to the number of
Okay.
I don't know. I
So
don't
let
even
me tell you
understand.
about line of best. I understand what you're saying. Let me tell you about line of best fit. Line of best fit is not necessarily how many points it crosses. Line of best fit is how close are all the points to the regression line in general. So you create a line of best fit to make sure that your residuals are not plenty. That is how you create your line of best fit. And like I told you, residual is the distance between the values of y and the point. Or okay, let me not even use residuals, let me just use data points. So how much of distance do you have between each of the data points and line? Now I know what you're saying. Assuming we did this, we could have done this, right? Like put the line this way. So we could have put the line this way. Okay, put the line this way, make it cross a lot of lines. So now see the distance between these data points and the line that you're going to be drawing is going to be really wide. But then putting it here, these data points, look at the distance, and then see we still have a reasonable distance between this and these ones. So line of best fit is not necessarily how many data points it crosses. I mean regression line, sorry, not line of best fit. Regression line is not necessarily how many data points it crosses. It is how close are the data points to the line. That is what regression line is. So regression line is used to predict values of y, and then if you're using regression line to predict values of y, they have to be close to the regression line. So that is about regression line. So not necessarily how many points it crosses. So I hope I was able to clear that.
Yeah, you were. Thank you very much.
Okay, you're welcome. So okay, so they were doing something here. I'm following your manual. I'm on page 266. They got the regression value. So this LM is used to get the regression value, right? This app line is used to construct the line. So app line is constructing the regression value, or the regression values. So that's what app line is doing here. So let me just put this into petrol reg. Okay, let me just do this, and then let's see what petrol reg is. That's the regression line. So see, this is the intercept. So they gave us the value of the intercept, and please give me a minute, please. I'm so sorry. A bit urgent. Okay, so this is the intercept, and this is the coefficient of the regression line. That is okay. So I got a definition for that. A coefficient is the value that multiplies the predictor variable. So if the sign of your coefficient, okay, is the sign of your coefficient indicates the direction of the relationship between the variables. So here you see that the sign of the coefficient is positive, right? So it means that our variables are positively correlated. And then if it's negative, it means that our variables are negatively correlated. So this is these are regression values. We have the intercept and we have the regression coefficient. So I think I told us how to calculate the regression coefficient the other time. So this value was calculated from that formula, the regression coefficient formula. So whether it's positive or negative, you can easily determine whether your values are positively correlated or negatively correlated, depending on the sign of this coefficient. So this is the intercept and this is the value that was calculated from the formula. There's a formula for calculating regression coefficient. Okay, so putting this, using upline on this would give you the regression line. So there are a lot of things that have gone into using these functions, right? That you don't have to manually calculate anymore. So if we did is it upline now on this? I want to be sure. We would get the regression line. If I remove this, and okay. Just like you did the whole of the formula, you will get the same thing. So it will also give you the regression line. So upline helps you to calculate the line of best fit in your data points and it plots it together. So you're doing an upline on the on the regression, on the relationship between this and this. That is what it's doing. So upline basically helps you to construct a line of best fit in your points. And then we already calculated calculated the correlation between this and this in this formula. So the upline now takes this formula and gets a line of best fit. So that is what upline function does. Upline can be used to draw lines on any kind of chart, but then upline does, it calculates it based on what you want. So you can have a sum of x and y values and then use the upline function to put a line on the x and y values. It gives you what you want. It could also be a curved line. Upline doesn't necessarily have to be straight. But then because we are doing this on a regression formula, it's going to give us a straight line, which is a regression line. So the upline function is very powerful. It gives you what you ask for. Okay, so this is about getting the regression line for this particular data set. Then we also, okay, you can also check the summary statistics for this regression for petrol reg, which is the regression coefficients that were calculated. You could also get the summary statistics for it, error, t-value, and all of that. A lot of statistics, multiple R-squared value, adjusted R-squared value, all those things that you would have used formulas to calculate, residual, standard error, and so on, p-value. So all of these things you can get from getting the summary of this regression function. And then another thing you can do is analysis of variance. You could also create some other plots from this regression function. So you could do plot petrol reg, and this would give you a lot of, okay, so we're going to calculate, okay, let me just do this first. Plot petrol reg. So we would have different plots. So let's put all the plots on a page. So we're going to have 4 plots. So let's change the layout of our page. So layout, let's create layout as a matrix of 2 by 2. So we have 4 values and 4 charts, and then we want them all displayed at once. So 2, 2. So we've changed the layout. So now let's plot petrol reg again. Okay, let me clean this first. Can I just clean everything at once? Yeah. So let's change the layout and then let's plot this. This is not what I want. Okay. So this is where to change the layout. You want a matrix of 1 to 4, then you want it 2 by 2. So I've changed the layout and then I'm plotting this. So I'll have all my four charts represented here. So when you're plotting a regression coefficient, you would have 4 charts, and these 4 charts mean different things. I might not be able to go into details, but then for example, this is just plotting all the residuals by the fitted values. So there's a formula for calculating fitted values. It's in your manual somewhere. I think I'm trying to remember the formula for calculating fitted values. There's a formula you use to find fitted values, just like you found residual values. Oh, we didn't find residual values. Okay. So let's quickly check residual value. So residual, this is the formula for getting residual, petrol reg. So you want to see the differences between the normal y values and the y values on the regression line. So these are the differences. So for the first y value, this for value 2, value 3, value 4, and so on. These are the residuals, okay? And then we also have, all of this will have applications, but then we can't talk about all of that. Then there's a formula for calculating the fitted values too. I'm trying to get that. So it's fitted, it's FITTED. So fitted values, petrol reg. This will give you the fitted values. So the fitted values are you're predicting, it's like you're predicting the response variables. So that's what fitted values are. You are predicting the response variables. You are using a formula to predict what the response variables are when you use the values of the predictors. So when you put in some x values, you are predicting some of the y values based on x values. So these are the fitted values, okay? Predicting the y values based on x values. These are the values that would give you. And then the residuals are the differences between the normal y values and the values on the regression line. So when you're checking these two together, when you're checking these two with one another, it could give you insights into whether what the values you use on your regression line and the values that can be predicted, whether they are very well correlated with one another. You can use this to see how well correlated your data is. If your fitted value is I think if it is positively correlated, that means you're on the right track. If it is just a little correlated with one another, you might need to recheck your data points again. So if you look at this, I would like to give us the correct interpretation of what this graph is. But then basically that is what residuals and fitted values are. And there's a very good interpretation of this graph that I will not be able to interpret now. But then we can check this later. So this can be very useful to check how well fitted your values are with one another. And then there's this scale location graph. If your scale location graph is horizontal, it means that you have a uniform variance. So uniform variance means that your values are not extremely distributed. They are well correlated with one another. And as you can see, this doesn't go straight up. It's almost uniform. Although it goes up and then becomes uniform. So it means that your your data is not uniformly variant. It's the variances are different. But then that's what this graph is used for, scale location. Then we have this normal QQ plot. You are plotting quantiles against one another, and then this also has its application. Then we have the residuals versus the average graph and all of that. So all of these are regression graphs, and then they have their applications in statistics. Then we also have, let me see. Okay, so there's also the multiple linear regression that you use to check different values against one another. So you have different explanatory variables. You have different explanatory variables, and then you want to check how well correlated they are with your y variable. That's where you use the multiple linear regression. But because of my meeting, I might have to run now. Let me quickly check something, please. Okay, I might have to run in the next 10 minutes, but then let's quickly see what we can do on multiple linear regression. So for multiple linear regression, so let's plot, let's find multiple linear regression using this same data. LM, we're checking the regression for petrol data against this. Then petrol data so this is cost statistics. So I'm sure some of us are like, what the heck are all of these? This is statistics. If you want to be a data scientist, you have to go and understand what all of these things mean, because you will definitely have to create models and predict values. So you definitely have to understand all of this, but we cannot cover everything in the class. That's just the truth. But understanding the basics is the main thing, and then you can still go back to check them out on your own. Okay, then petrol data. With this, so we want to check the relationship of this with this and this. So this, we are using two explanatory variables now and one response variable. Okay, then let's check what this gives us. Okay, so we have this for the first one, we have this for the second one. So you see -24. So this shows that it is negatively correlated with y. And then we have the intercept as this. We have this, we have the intercept as this. Then okay, what else? Okay, yeah, that's all. So we can plot, okay, we can try to plot this and this and see what it looks like. So let's plot them. Let's plot this and the second value. Let's see what it looks like. So okay, so what I'm going to do is I'm going to clear this. And then I'll plot this one, this first one that we had with the purple one. Then I would plot this one with red. But for this one, I would have to use, I think points. Should be points. Yeah. Then I don't need this title because I just want to add it to the graph. I'm not plotting a new graph. I want to add it to the graph I already have. But then I want to use not petrol pump driver's license now. I want to use petrol tax cents per gallon, the one that gave us the -24. So that's what I want to use now. And then I want to add it to the chart. Okay. So let's see. Oh, it's not plotting. I'm not sure if it's points or something. Can someone remind me what you used to add a second variable to a scatter plot? We've done it, though. People should remind me now. I want to add another scatter plot to the chart. Somebody should be able to remember. We did it when we're creating plots. Nobody.
Sorry, ma, what did you ask?
Okay, so I want to add this other variable to the chart. I want to add this other variable to the chart. This other point, I want to add it to the chart. So I plotted this against this for the first one. Let me just bring it down so you see what I'm doing. So you know what, we're dealing with multiple regression, okay? And then when I first check the regression for when I checked regression for the first one, I did consume mil gallons against pub drivers licenses only. But now I want to do multiple regressions. So I added petrol tax cents per gallon. Like you can see, I used the plus sign and I added this. Okay, so on checking this, you can see that we have two explanatory variables now. We have one with positive, which is proportion pub drivers licenses, and we have this one. Okay, so now I want to show us the plot for this one, for this petrol data, for this pub drivers, and then I want to add this other one to the plot too. So I want to join this. I've plotted this, then I want to put this same this other one on this same plot too. That's what I want to do. Does anybody understand what I just said?
No, I did not get your question.
I think I understand.
Okay.
You want to plot a scatter plot with 3 variables.
With 2 explanatory variables.
Okay.
Yes. Yes. And this is the formula for putting it, but it's not working. Okay, let me try to label the X as something else. And the Y as something else. So I want to plot this, and I want to plot another scatter plot on it. Okay, it's not working. I don't know why it's not working. But then I wanted to show us why that one is negative, why the other one is negative. So we had one regression coefficient giving us negative, which means that it is negatively correlated. And I want to show us why it's negatively correlated. I want to show us the direction of its points on the graph. So okay. All right, since that is not working, or am I making an error? I don't know. This is X and this is Y. Okay, it's like nobody's even ready to contribute to what is going on here. Okay, that's fine. So what I wanted to do was I wanted to plot both of them and see what it looks like. But since we can't plot both of them, let me just plot this only. Let me plot this singly. So let's plot this against this, and then let's see the color. So as you can see, this if you check the regression coefficient here, you will see that this gave us minus 24.31. Now, if you were to put a line here, it will be negatively correlated. So your sign determines how whether your data is negatively or positively correlated. Now let me put a line on this, or maybe because one is negative and one is positive, that's why it's not plotting it on the same graph for me, because most of the time you plot both positively or both negatively correlated on the same graph, so maybe that's why. And then maybe the data points are quite different from one another. So see, this is 3, 4, 5, 6, and then maybe that one is something else. Quick confirmation. Let me just quickly confirm that. So that's the way to check.
This one is actually
Okay,
in
see,
decimal
this is
format.
0.4 to 0.9. Okay, so you see that. So that's why we cannot see it plotted. And then this is 3 to 9. So you see they are different. So that if we were to plot two of them together, one will probably be way behind. So we cannot plot them on the same axis. They don't have the same values. So that's why we don't have this being plotted. But looking at this individually, you can see that this is negative. Okay, and let's put an up line to this. So if we're to put up line to this, let's calculate the regression value first, and then create the up line. So I'm going to change this to sorry, not that one. So it's y to x. When you're calculating regression, you do y to x. That's where you calculate regression. So let me do petrol reg 2. Okay, so let's calculate the regression of this, and then let me see what it's like. You see, minus 5, 6. So you see, minus 5 is negatively correlated. So let me see the up line of petrol reg 2. So you see, it's negatively correlated. So you see the line. So that is about checking multiple correlation. Assuming we had both our x values in the same, one is decimal and one is not decimal. That's why we can't plot them together. We could have been able to see both of them on the same chart. So that's about multiple linear regression. That's why I said all these things, you still have to go back and check them out. Check them out on your own. We can also do it for 3. You know, we did it for 2 here. We did it for 2 here. We did it for this and this. We can do it for this, and all of the other field variables that we have. We can do it for all of the other 3. Then so lab 2 is telling us, what's lab 2 telling us to do? Implementing simple and multiple linear regression. Okay, we've done that already. We don't need to repeat that again. So this is showing another kind of data set. It's still similar to what we just did. It's very similar to what we just did. So for lab 3, let us try it on our own. I've explained multicollinearity to us. So and then the lab exercise is explicitly written here already. You already have the solution. The data set 2 is also present in your Hadoop environment. So you can look for the data set in your Hadoop environment and follow through to work on lab 3. You could also go back to the manual and check some of these functions. But I think I've covered majority of the functions. Okay, I remember I've taught us what LWD is. You want to change the width of your line. You want to make it thicker. I've told us what LTY is. LTY is your line type. So if you wanted to change your line type, I remember explaining how to do that to us when we're plotting graphs and all. So all of these things are what are in the textbook on pages 29 to 33. So you can go back and check all of this, but I've explained most of the functions that are being used in regression. But please work on lab 3 on your own. Work on lab 3 on your own, please. Work on lab 3 on your own. And let me know if you have any other questions in the next class. So that'll be all for this class. If you have any questions, let me know. Let me know if you have any questions as regards what we've done so far. I'm sure it's feeling more difficult to some people now. We are in the second textbook, so you have to tighten your seatbelt. It cannot be like the first one, okay? And then we're trying to meet completing this textbook by the end of this month. So I cannot do everything that is inside your textbook. I cannot do everything inside your textbook. So definitely you will have to go back to check your textbooks and get more knowledge on these things. But then basically what I've explained today, do you to a level understand what regression is? I need comments, please. Don't keep quiet. From what I explained today, can you give the fundamental explanation of what regression is, what simple and multiple regression means, how to get a regression line, the functions to use when you are trying to get regression, the regression coefficient, how to determine when you have a negatively correlated or positively correlated variable, some formulas to use in regression, some terms you use. I need comments. Someone should just let me know that I explained something that you understand today. At least before you go back to understanding or to reading up, to doing lab 3, and then also checking things on your own. Yes? Okay. Daniel.
Thank you very much, Ma. Yes, I do understand. I understand what you taught us today, the simple regression and the multilinear regression.
Okay.
Even though, yes, in R it's looking more like we're doing soft maths. Like it's we are not using the exact same formula, but it's looking like more like that compared to
Really?
where you're doing it in Python, just importing libraries and just doing it straight.
Okay, in Python, you just import library and just does it. But here you have to like still add some things and all of that.
Yeah. Yes. So
okay,
that's like softer maths.
soft maths.
But
Okay, R is a
thank you.
statistical tool. Huh? You said?
Yes. So thank you very much. I get that now.
Okay, you're welcome. So R is a statistical tool, and then you don't just go off into importing libraries in R. In R, you actually perform these things because R is used by statisticians. They want to know how you got this and that. They don't just want you to give them a result. So R still makes use of statistics, but in a more sophisticated way. You don't have to do all of these SSX formulas that I was explaining earlier. All you have to do is to just put some functions together and make it work. But in Python is not a statistical tool. Python is a programming language. In Python, you just import some libraries and libraries do the calculations for you. So R is more of a statistical tool. So yes, you will do some maths in R, and then you have to be mathematically sound, or you have to want to learn to be able to understand R well. So R is used by statisticians, and as data scientists, you have to be a statistician because you'll be asked some questions. If you're using Python and you import one function and it just does that, they say, okay, you just imported, you did this, you got this value. So how did you get the value? What is the basics of you getting the value? What did you add to what? How did you multiply the values? What did you have as a regression coefficient? What was your slope? What was your this and that? You won't be able to give all of those answers if you were just using Python. So R is a statistical value, and then as data scientists, you have to be able to give explanations to your values or to your variables. So that's why as data scientists, they tell you to understand how to use R well before you jump on using Python that is extremely simple, that you just put in functions and get your value at a go. So data scientists have to have the ability to be able to understand the underground mathematics. That's why I was explaining all the formulas earlier. Understand the underground mathematics behind all of these things, and then be able to perform the functions too as well. So that's just it. Any other questions or comments? Talk. It's getting difficult. It's looking more complicated. Say it. Don't hide it. You don't have to hide it. If you're hiding it, then I don't know, but then just say it. Like, make comments so that if you make comments, you can have, there could be somebody that understands this thing better, You could, the way you organize extra classes within yourselves, you could also organize extra classes within yourselves. That's not a big deal. So you have to speak out. But then you could just like keeping quiet. I'm the one that is always talking. My mouth is paining me safe. Okay, I'll mention 2 people's names before I run away. Let me see.
Sorry about your mother is paining you, actually.
Thank you. So you don't want my mouth to pain me again. Because I was planning to call you. So what do you have to say?
Well, like Daniel said, soft math. But
soft math.
Just
okay.
I just know you just have to give it time actually.
Yes.
A lot of these things, they are easier on Python and they just kind of look strange here. But just always
you also you also write Python, right?
A little, not like Daniel anyway. Daniel is a pro.
Okay, Daniel, pro. Well done, sir. Yes. Can continue.
So what was I saying? It's just always very, I don't know. I don't like it whenever I hear that I can't do everything in class. People have to go and learn on your own. All our trainers say that, and I be like, oh Lord, where do I start from? There's always many things to learn on your own, and then you have to prepare for exams, different assignments, and all. But at the same time, you just have to face it. We are there already, so just have to give it time. But it's not that hard. But
it's not.
Yes.
It's actually not. If you are reading,
I need you interesting. So
okay.
Yeah. Thank you very much, ma'am.
Thank you too. So, like I said, I'm always saying that we have to read some things on our own, and it's the fact. Even if I teach you the old textbook, if you don't go back and read on your own, you will still not understand it, because everything is not inside this textbook. There are a lot of things that are not in the textbook, and then we're trying to become a data scientist in 2 months or in 3 months. It can't work. We cannot get everything you need. You have to still do some checkups and some read-ups on your own. So that's basically it. That's why when we're talking about Power BI the other time, I was like, are you practicing these things on your own? Or after class, you're just like, that class was stressful and I did not understand what they were saying. So I'm not